In the last video, we explored what IPC is, broke down different interaction styles, talked about the importance of API-first design, and looked at synchronous communication using REST and gRPC. Now, it's time to look at the other side, asynchronous message-based communication. In this video, we'll unpack how messaging works, and more importantly, how to design a messaging architecture without tying it to any specific technology. We'll then compare brokerless versus broker-based messaging setups and look at how to choose the right message broker for your system. Alright, let's get started by understanding how messaging actually works under the hood. In a messaging-based setup, services exchange messages asynchronously, meaning they don't wait for an immediate response. When a client needs something from another service, it sends a message and moves on. If a response is needed, the service replies later with a separate message. Since this is asynchronous, the client doesn't block. It's built to handle the response whenever it arrives. Most systems use a message broker in between, like Kafka or RabbitMQ, which routes messages from the sender to the receiver. But you can also have a broker-less setup, where services send messages directly to each other. One of the most practical ways to think about messaging comes from the book Enterprise Integration Patterns. It describes messaging in terms of message channels, a concept that makes it easier to reason about how services communicate. Here is how it works. A sender, which could be a service or application, writes a message to the channel. Then, a receiver picks up that message from the same channel. Pretty simple, right? The channel acts as a bridge between the sender and receiver. Let's break down what a message actually contains. Every message has two parts, a header and a body. The header is basically metadata, a bunch of name-value pairs that describe the message. It could include a unique message ID, maybe a timestamp, or even a return address specifying where to send the reply. The body is where the actual data lives, and it can be text or binary format depending on your use case. Now, not all messages are the same. There are three common types: document messages, command messages, and event messages. Document messages just contain data. The receiver decides what to do with it. A typical reply message, like after a command is processed, often falls into this category. Command messages are like remote procedure calls. The sender is asking the receiver to perform an action, with any necessary parameters bundled in. Event messages are like signal that something has happened. For example, order placed or customer registered. These are common in domain-driven design and event-driven architectures, where you want to react to changes in state. In modern microservices, commands and events are used extensively. They help decouple services and build more flexible, reactive systems. Now, let's talk about channels, the core mechanism services use to send and receive messages. Think of a channel as a pipe that connects a sender to one or more receivers. The sender's business logic talks through a sending port, which hides all the low-level communication details. The port is usually backed by a sender adapter, which actually pushes the message into the channel. On the other side, the receiver has a handler adapter that listens to the channel. When a message comes in, it passes it onto the receiver's receiving port, which then triggers the actual business logic. What's neat is that multiple senders can send messages into the same channel, and multiple receivers can subscribe to it as well. So it's very flexible. Now, there are two main types of channels you deal with: point-to-point and publish-subscribe. Point-to-point channels ensure that each message is delivered to only one receiver. This is commonly used for command messages, where a specific action is expected from a single service. It maps to one-to-one interaction styles, like a task queue where only one worker picks up the job. Publish-subscribe channels broadcast the message to all subscribed receivers. This is perfect for event messages, like when an order-placed event is sent out and multiple services like billing, inventory, and notification all need to react. One of the great things about messaging is flexibility. It can support all the interaction styles we discussed in the last video, both one-to-one and one-to-many, synchronous and asynchronous. Some of these styles are built right into messaging infrastructure, and others you can layer on top depending on your system needs. This versatility is what makes messaging such a powerful tool in microservices architecture. When a client and service communicate, the interaction might be request-response or asynchronous request-response. The difference? In the first case, the client waits for an immediate reply. In the second, it sends the request and moves on. No waiting. Messaging by nature is asynchronous. So even if a client eventually expects a reply, it doesn't block. Instead, it works by sending a command message to the service over a point-to-point channel. The service processes it and replies back on a separate channel owned by the client. For example, here, the client sends a message to the service through a request channel. This message includes a unique message ID, a return address, basically the name to the reply channel where the service should send the response, and the actual message body, which contains the request data. The service reads the message from the request channel, processes it, and then sends a reply message back to the client via the specified reply channel. And this reply includes a correlation ID, which matches the original message ID from the request. This helps the client figure out which request the reply belongs to. And it also has the reply body with the result or outcome. The client listens on the reply channel and uses the correlation ID to match the incoming response to the original request. This setup allows fully asynchronous communication, where the client doesn't wait around but still gets the response when it's ready, and everything stays loosely coupled and scalable. Now, if the interaction is one way, where no response is needed, it's even simpler. The client just sends a message and the service handles it. No reply involved. And when you need to notify multiple services, messaging makes it easy with publish subscribe. For example, the order service can publish domain events like order placed to an order channel. Other services like delivery or billing can simply subscribe to the channel and react to the events in real time. This kind of decoupled communication is what makes asynchronous messaging so powerful in microservices. I have previously made videos on both point-to-point and PubSub, so do check them out if you need more clarity. Now, there are two main ways to implement asynchronous messaging: brokerless and broker-based. In a brokerless setup, services talk to each other directly. No intermediary in between. Tools like gRPC makes this possible. The advantage? Message goes straight from sender to receiver, which means low latency and less network overhead. You also avoid the complexity of managing a separate message broker. But here is the catch. Services now need to know each other's locations. So you will need a discovery mechanism in place. And if either the sender or receiver is down, the message is lost. And implementing things like guaranteed delivery, retry logic, or message durability becomes a way more complicated. On the other hand, with a broker-based architecture, you introduce a dedicated message broker like RabbitMQ, Kafka, or ActiveMQ. This adds a layer between services but gives you so much more in return. For example, reliable delivery, built-in retry and persistence, loose coupling because services don't need to know who they are talking to, and you get better availability since the broker can queue messages even if the receiver is temporarily down. And yes, it does add some operational overhead, but for most real-world systems, especially at scale, a broker-based approach is the safer, more resilient choice. And that's why it's the go-to architecture for enterprise applications. Now, each message broker implements the idea of channels a little differently. For example, JMS brokers like ActiveMQ use queues for point-to-point and topics for publish subscribe. RabbitMQ, which is AMQP based, uses exchanges that route message to queues. Kafka and Kinesis use topics and streams. AWS SQS only supports queues, but you can pair it with SNS to enable publish subscribe behavior. Cloud services like Google PubSub and Azure Service Bus support both interaction styles through subscriptions. So, while the underlying implementations differ, most modern brokers support both the point-to-point and PubSub communication styles, except AWS SQS, which is strictly point-to-point unless you combine it with SNS. And there are same solid reasons why broker-based messaging is a go-to strategy for microservices. Things like loose coupling, because clients just drop messages into a channel. They don't care where the services lives or how many instances exist. No service discovery needed. It has built-in message buffering. Messages wait in the broker until a service is ready to process them. So if the service is down or slow, nothing breaks. For example, your online store can keep accepting orders even if the fulfillment system is lagging behind. It supports multiple patterns. You can implement request response, one-way commands, event publishing, whatever the use case demands. And unlike RPC, which tries to make remote calls feel like local ones, messaging forces you to think explicitly about the realities of distributed systems. Of course, messaging isn't free of downsides. It has potential bottlenecks because the broker could become a performance checkpoint. That said, modern brokers like Kafka and RabbitMQ are built to scale. But if your broker goes down, communication stalls. So it's crucial to run it in a high availability setup. Operational overhead is one more moving part. You will need to install it, configure it, and monitor it, and keep it running. Still, the benefits far weigh the trade-offs, especially when you are building resilient, decoupled, and scalable microservices. In short, if you are serious about async communication, a message broker is the way to go. So far, we have explored asynchronous messaging in microservices, how it works under the hood, the role of message brokers, and why broker-based architectures are often the better choice for building scalable, resilient systems. We also looked at messaging patterns, message channels, and how different brokers implement point-to-point and pub-sub communication. But this is just the beginning. In the next videos, we'll dive into the real-world design challenges you'll face when building message-driven systems, like competing consumers, preserving message order, handling duplicates, writing idempotent consumers, tracking messages across services, and even combining messaging with transactions to boost reliability and availability. And if you're enjoying this series and want to keep leveling up your system design skills, make sure to like, subscribe, and check out the full playlist link below. See you on the next one.